Function notation that we just went over is especially helpful whenever you have an actual formula to associate with your functional relationship. For example, let's say we were talking about the area of a circle. Hopefully we know that the area of a given circle is equal to pi times that circle's radius squared, where, let's remember, the radius is the distance from the center of a circle to the edge of the circle. So we can think of area of a circle as a function of r, right? It's a function of r because what does the area of a circle depend on? Well, it depends on the length of that circle's radius. So in this function that we're going to create, the input is going to be r, the output is going to be the area. To reiterate, the independent variable is going to be r, the length of the radius, and the dependent variable is going to be the area of the circle. So let's use the letter a, and let's make a function a of x equals pi. Actually, let's do this even. Let's make a function that's a of r, and let's actually use the variable r, and let's say a of r is equal to pi r squared, pi times r squared, okay? This says a of r, or area as a function of r, is equal to pi times the radius squared. So if we wanted to know what is the area of a circle with a radius of 1, we would calculate a of 1, and that equals pi times. So if we look at wherever the variable appears in the formula for the function, and if we look inside the parentheses and see where to see what number we replace that variable with, wherever that variable occurs in the function, we are going to replace it with the value, right? See what I did here? Our general formula was a of r equals pi times r squared. We're evaluating for r equals 1, so wherever r appears in the formula, we are just going to replace it with the number we're using. So a of 1 equals pi times 1 squared. That's equal to pi times 1 times 1, right? Which is just pi. All right, that was a pretty easy example. What if we wanted to know the area of a circle with radius length? Let's say 3. Well, that's going to be a of, remember our original function was a of r, so we're going to replace r, the variable, with the actual value 3. So then we're going to write out the formula associated with the function, and wherever the variable r appears in the formula, we're going to replace it with the value 3. Make sense to everyone? So we'll evaluate that as pi times 3 squared is what? 3 squared is 3 times 3, which is 9. And we can just write that as 9 pi. All right, let's try one more. Let's try the area of a circle with a radius of length, let's say 7.20. All right, let's try the radius of 7.20. That means r is 7.2. So we are going to evaluate, let me get a different color. Let me just get a different color here. So we are going to evaluate a of 7.2. Whoops. A of 7.2, which is going to equal pi times the value 7.2 squared, right? So that's just pi times 7.2 squared is 7.2 times 7.2. We're going to get pi times 51.84, which we can write as 51.84 pi. Okay, everyone, let's do a couple more examples using functional notation and formulas for our functions. So let's say we have the function g of x equals 5x minus 2. That means g of x equals 5 times x minus 2. And what if we were given this table and we were told to fill out this table for the given values of x? All right, that's not hard to do. We just need to take our function g and evaluate it for each of these given inputs, 1, 2, 3, 4, and 5. So let's start off by evaluating, let's say, g of 1. So g of 1 is going to equal what? That's going to equal 5. So if our formula is 5 times x, that means we're going to evaluate 5 times 1 minus 2. Okay, 5 times 1 is 5 minus 2 equals 3. All right, so we know that g of 1 is equal to 3, so we can fill out our value 3 in the first row on the g of x column. All right, let's evaluate g of 2. All right, whoops. I do want to keep using different colors, so let me adjust that. G of 2, if it'll actually write. G of 2, there we go. Okay. G of 2 is equal to 5 times 2, right? We're replacing x wherever it appears in the functional formula with the value 2. So 5 times 2 minus 2, that equals 10 minus 2, which equals 8. We got our second row done here. Let's evaluate g of 3, right? I keep forgetting to change my colors. G of 3, that's going to be 5 times 3, right, minus 2. That's going to be 15 minus 2, which is going to be 13. All right, let's evaluate g of 4, which is going to be, according to our formula, 5 times 4 minus 2, which is going to be 20 minus 2, which is going to be 18, right? We got 18 here. And finally, we're going to evaluate g of 5, and we're going to get 5 times 5, right? 5 times 5 minus 2. It's going to be 25 minus 2. That's going to be 23. And that's all there is to this. All right, let's practice with a somewhat more complicated function, okay? So here we have the function h of x equals what? Equals x squared plus 3 divided by x. All right, so this is where we're going to have to keep our order of operations in mind, right? All right, so let's try to fill out this table for the 3 different inputs of x, 1, 2, and 3. Okay, let's try to evaluate h of 1, okay? That's going to be equal to, well, if the numerator of this function is x squared plus 3, that means we're replacing x with 1, so this becomes 1 squared plus 3. And if the formula says divided by x, that means we're dividing that numerator by 1. Okay, 1 squared is 1 times 1, that's just 1. So the numerator is 1 plus 3 divided by 4. It's not bad, that's just 4. Whoops, my bad. That's not divided by 4, that's divided by 1. So this value is just 4 over 1. Oh my gosh, why do I keep doing that? It's just 4 over 1, which just equals 4, right? So to summarize that, that means that h of 1 equals 4. Okay, let's try to evaluate h of 2. All right, let's plug in that value of 2 into our function of x. This is going to become 2 squared plus 3 divided by 2. That means that 2 squared is 4, so this is going to be 4 plus 3 divided by 2, which is going to be 4, 5, 6, 7 over 2. And that's fine. You can definitely have a fraction as an output. So that means that h of 2 equals 7 over 2. So we can fill in 7 over 2 over here. And let's finally try to evaluate h of 3. So that's going to mean we have to plug in 3 into our formula. That's going to give us 3 squared plus 3 divided by 3, right? So that's going to equal 3 times 3, or 3 squared, is 9. So we're going to have 9 plus 3 over 3. 9 plus 3 is what? 12, right? So that's going to be 12 divided by 3, which is going to be 4. So that means h of 3 is equal to 4. And we can place that right there. Remember that this is okay. These two results, this is perfectly fine, right? Because let's remember the rule of the function. The rule of a function is that one individual input must only produce one output, right? But you can have different outputs produced by the same input. That's what's going on here. We have the output of 4 produced by two different inputs, which is fine, right? Let's remember what wouldn't be fine is if one individual input supposedly produced two different outputs. That would not be okay, but what we have going on here is totally fine.